This is the bonus part. It's all about arrays. What's an array and what are things like memory allocation, static, and dynamic, and how to create an array. We're going to start defining an array. Remember this representation. These lines actually represent, let's say, your computer memory. Your computer memory has what I'm gonna call memory location, where each memory location has an address and a data it can store. An array is a collection of contiguous allocated memory locations. You can tell the compiler that you want to allocate a memory at runtime, or you want to allocate some memory to your program at runtime. We have some libraries for that. For example, the stdlib library, we can request memory addresses. For example, we can tell at runtime, we can say, okay, we want to allocate 4 memory locations for our program. Then we can set the values inside those memory locations. I'm going to show you the process by which this thing works. In the code side, I'm going to include the stdlib library. Then there is a function called malloc. The malloc function will request some memory space for your program at runtime. We can say, for example, we want to reserve enough memory space for storing integer data types. Then I'm going to say we want to multiply it by, let's say, 5. So this will allocate 5 memory locations contiguously, and all of these memory locations can store integer data type. On the right side, I'm going to update the lines. So here we know that each of these memory location can store an integer data type. Now, the next problem is how to get access to those memory location we just allocated to our program. The malloc function actually will return the address for the first allocated memory location. Since these memory locations are contiguous, it means we just need to add up 1 to the first memory location to get the address of the second memory location. Then add up 1 to get the address of the third memory location. Then add up 1 again to get the fourth address. Then add 1 to get the fifth address. The malloc function returning an address means that we need to define a variable that can store this address. So I'm going to define a variable named p. Then add a star sign to let the compiler know that the type this variable can store is an address. So somewhere in your computer hardware, an address for the p variable will be allocated. Then let's say p represent the memory address and has the value for, let's say, the memory address data type is is data type is, let's say, a pointer data type. So since it is storing the address for the first element of these allocated memories, then the type should be a pointer to an integer data type. For example, if the address of this first memory location is, let's say, 0x055f, then the value stored in the variable p would be equal to 0x055f. So we use the variable p to remember the address of the first allocated memory location. So let's store that in the variable p. Great. Now that we know what is the address of the first allocated memory location, we can set the data on those memory locations. I'm going to say, then we can use the dereferencing operator. For example, let's say P start sign P equal 10. This will tell the compiler here in the variable P, we want to get the value stored in there, and the value stored in there is an address. Then we use the dereferencing operator to get access to the memory location. Then we assign the value 10 to the data field of that memory location. So the first memory location, or the first allocated memory location, will be having the data field set to 10. Then we can add 1 to the already known address. For example, 1 to get the address for the second allocated memory location. We can say 12. I need here to use the dereferencing operator to let the compiler that we're assigning the value to that next address. Then we can then add 2 to get the third address, then assign the value, for example, 13. Then P plus 3, which means the first address plus 3 will give us the address of the fourth contiguous memory location, and we can set it to 15. Don't forget to use the dereferencing operator to let the compiler know you want to change the value stored in the memory location. And the last one, we can say P plus 4 to get the address for the fifth memory location and set it to 16. We can continue like that. For example, we can say P plus 5. Then we assign a value. Let's say 100. But warning, your program could crash because of this line. These contiguous memory locations are the only one our program has access to. So by adding or trying to access a sixth memory location, which is not allowed for our program, the operating system might kill the program. So we want to make sure that we don't exceed the number of allocated memory spaces. So I'm going to delete this line. The next step is to display the values stored in this memory location. So I'm going to start by displaying the address, then display the value. Printf. So the first address would be like that. the data stored in it. It is an integer data type. Then we type in P, then we use the dereferencing operator to let the compiler know we want to get access to the memory address value, to the value of the memory location I want to set. Then I'm going to copy this and pass it 4 times. 1, 2, 3, 4. So here we have the second allocated memory location, the third memory location, the fourth memory location, and the fifth memory location. Then we're gonna use the dereferencing operator on each of these memory addresses. Three, and then 4. I'm going to change the format of the display. Now let's run this program. So here, as you can see, we have these memory locations, and we see that these memory locations are kind of contiguous. This is the representation, the hexadecimal representation. So by adding 1 to the first memory location, we get the address for the second and the third, the fourth, and the fifth. So this is what we've got here. What we did is allocating memories at runtime. So when you allocate memories at runtime, the compiler don't know when you want to free up this memory or release the resources. So we have to explicitly release the allocated memories. So that is for allocating memory dynamically. And this actual P represent an array. And I can even change the name of the variable. It's not actually important. I'm going to say array. And here also, we're going to say array. And then on the other side, we're going to say array. So that is an array, the name of the variable. So the name array it is just for readability, so that we know that this variable array is a pointer that points to a block of allocated memory locations. Now there is more simple notations. For example, instead of using address plus the number, then let's say assign a value, this notation, we can use a more simpler way. This is called array subscription. No, array subscripting. So we can use the array subscripting operator instead. For example, we can say array then 0, which is equivalent to saying that array plus 0, then using the dereferencing operator. So we can say array, then subscribed, and assign the value 10. The same goes for the others. So here we can say 12, and I can update each of these lines. So this line will be replaced. The third line will be replaced by array 2, and this one will be replaced by array 3, and this other one will be replaced by array 4. So this tells the compiler to access the memory location, add 0, then use the dereferencing operator, then assign the value to the corresponding memory location. We can use the same thing here for these lines. So that will be array 1, array 0, array 2, array 3, and array 4. Now let's run this program. We now have the same output: 10, 12, 30, 15, 16, in the same order like here. So the array subscribe thing is more simpler than using the referencing, dereferencing ways, but it might come handy in some situations. Let's say we want to look through this array or this list of addresses. I'm going to declare a variable that can store an address. I'm going to call it addr. It can store addresses for integer data types. Then next, we are going to set addr to array. So the value stored in the array variable, or the value stored in the memory location for the array variable, will be copied into the memory location represented by the addr variable. On the right side, I'm going to represent that. So addr will be representing a memory location that has an address and a data field, the same type as the array variable, and it will also be assigned the address, for example, 0x055F, which is the address for the first allocated memory location. I'm going to change this to array. So let's change the values stored in these memory locations by looping through the addresses. So I'm going to declare a variable, or let's say I'm going to say we can compute the last address. For example, the last address will be array plus 4. So we're going to say, while ADR is lesser or equal to array plus 1. So meaning that array plus 1 is where we should stop. It is, oh, this is array plus 4, the address of the last array of the last allocated memory location. Then we assign a value. For example, I'm going to set a current, oh, sorry. I want to say while So while the address is lesser or equal to the address of the last memory location, we're going to set the value stored in there to something. So I'm going to say the current address and use the dereferencing operator, the equal sign, and set it, for example, to 1. Then next, we're going to add up 1 to the ADDR variable. I'm going to delete these lines. So what's going to happen, or let's say I'm going to set all of the blocks to one header. So here we should see one header displayed. Let's compile this code and run. As you see, ADDR has been set to the first memory location stored in the array variable. Then we use this ADDR variable to look through the memory addresses. With the dereferencing operator, we've been able to set the value of each of these memory locations to one header. That's why all these are displaying one header, one header, one header, one header. So what if we want to update, or let's say change these values from a function? It's simple enough. I'm going to declare a function named initializeArray, and it has to receive the address of the first element of all those allocated memory locations. So I'm going to say ADDR. Then we're going to loop through and set them all to 0. But this function, all the init array function need to know, let's say, the number, the last address. So the last address would be the first address plus 4, or we can simply say we're going to pass in the length of the array. So for ADDR, or let's say while, we're going to, let's say, define an I variable and set it to 0. And then we're going to loop through the array 10 while I is lesser than the length of the array. So for I equals 0, I lesser than the length of the array I plus plus. Then what next? We say ADDR plus I. So here we're computing the value or the address of the next or the current memory location. So if I equals 0, then ADDR plus 0 would be the address of the first allocated memory location, plus 1, plus 2, plus 3, and so on. Then with the dereferencing operator, we can tell the compiler we want to set the value for that memory location. In our case, we're going to set it to 0. And then I'm going to delete the code here and type in init array, then passing the address of the first element of the array, and then the length of the array, which is 5. Let's run this code and see if it works. And what you see that we have the memory addresses and we also have the data field all set to 0. This implies that the init array can modify, or let's say any function, once it has knowledge of the memory address, it can modify it. So this is how arrays works. And you can use, for example, inside the init array, we can use the subscripting operator to update the values for each of these memory locations. ADDR, then the I variable, it will compile and give the same result. The data is still 0, 0, 0, 0, and we have the addresses here. So this is all about dynamic memory allocation. We can allocate, for example, spaces for older data types. For example, if you have knowledge of structures, you can define, you can allocate enough memory space to store those structures or whatever data type you've been defining. We know now what is an array, and we also know about dynamic memory allocation. This is actually dynamic memory allocation. There is another way of defining an array. This is static allocation. A static allocation means that when your program compiles, the memory is allocated because the compiler already knows how much storage space is needed. You use the malloc or the dynamic allocation when you don't know how much memory space you might need. But for now, let's see an example of static memory allocation. So when you use the static memory allocation, we can do it something like that. We type in the name of the variable, let's say array, and then we type in the number of allocated memory space we need. Let's say 5. So since this is known, the number of memory space is known at compile time, we don't need to free the space because the compiler already knows when to allocate and when to free or release the memory spaces. So here we've defined an array of 5 memory locations that we can access and modify as if we were working with dynamically allocated memory. Let's compile this thing and see if it gives us the same result. And here it is. We have the data field and also we have the values stored in those fields. I'm going to change the init array function and update it to, let's say, 5 or 15. Then let's compile it again and run. Yes, all the fields are set to 15, 15, 15. This is all about arrays as for now, and understanding the meaning of a variable or what a variable represents and thinking in terms of memory location can impact your understanding on pointers on whatever you need to get done on your C programming course. Thank you and have a great time.